So my name is Benjamin Mitchell. For anyone that doesn't know in the room, I work for Samsung Electronics in the game dev engineering section. And today I'm going to be talking a little bit about a specific title, which is Call of Duty. I hope that most of you in the room have heard of Call of Duty, and if not, I'll give you an introduction anyway. We're going to be speaking specifically about the Android version, and how we worked on it, how we brought it together with Tencent and Activision, how we made it into what it is, as it was actually quite a huge success, for those of you that don't know. So we'll be talking about what we did to actually bring that to mobile in the past few months. It's actually out now as of earlier this month. So before I go into anything super crazy, I'm going to introduce briefly what Galaxy gamedev does in the Samsung team. So Galaxy gamedev is Samsung's own game developer support program. So our goal, put into one sentence, is to help Android game developers bring amazing titles to mobile hardware and explode the mobile ecosystem, make it amazing. So we do that mostly through early adoption of these three sort of main technologies, one of which is Vulkan, which I'll be speaking about fairly extensively today. One of them is 60-volt programming and multi-threaded rendering. These are the same sort of things we bring to every main mobile game. We tell people this is amazing, this is what you should be doing. Generally speaking, it works. So we started in about 2016. We're now in 5 different locations, in San Jose in the US, in London in the UK, Kiev in Ukraine, Nanjing in China, and Seoul in Korea. I'm pretty sure you can guess which one I'm from. I am from UK, in case you didn't guess. We're currently working with about 25 engineers, all expert game dev, trained in the industry sort of thing, working with about 100 game developers and about 30 NDA partner deals. So those are game studios. So the key collaboration I'm here to talk to you about today is Call of Duty Mobile. This is one of our key collaborations of the year. So we have every year big collaborations with special partners. So we worked primarily with Tencent Games and through them a bit through Activision to make this really something special and make sure that it was as amazing as it could be. And today I'm going to be talking a little bit about what Samsung did on that side, and also a little bit about generally Call of Duty Mobile and why it's amazing. So I've split the talk into 3 main sections. The first bit is going to be an introduction to Call of Duty Mobile. I've got a cool video for you all to watch. It actually says at the end it's coming out soon. It's already out. So just ignore that bit. But the rest of it is still really cool. I'm going to introduce adaptive performance, which is something we at Samsung and also Unity are kind of pushing and hope to see as sort of the future of mobile gaming. And I'm also going to cover a section on Vulkan optimizations, which I've split into 2 sections. The first half is kind of just general Vulkan optimizations and tips, and sort of general tips and what we see every time on a game developer, what they should always improve. And then the second set of optimizations is stuff we did specifically for Call of Duty. They're very Unity engine specific, they're very Call of Duty specific. If you're familiar with Vulkan, those will be a bit more interesting, I hope. So yeah, let's get going. I think this is a video, yeah. Enjoy. Very quiet. I was expecting this to be more loud and amazing. But yeah, boom, 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 shoot, shoot, shoot. It's really cool. Imagine it's amazing, yeah. Thank you, tech guy. So yeah, like I said, ignore that coming soon, but it actually is already out. Other than that, yes, Call of Duty is a gun game. There's lots of bullets, lots of shooting. That's kind of it. So Activision and Tencent were working really hard on this because it was something they wanted to make as close to the console and desktop versions as possible. So the console and desktop versions are quite AAA titles. They're really high fidelity. They're really pushing the boundaries of what we can do sort of things. And we wanted to push the same thing on mobile. So this included down to the skin rendering, down to suit rendering, down to gun rendering, down to scene rendering. Everything had to be as close as we could possibly get it to the console and desktop level experience. So even every single gun, there are actually, the majority of the guns are, I believe, the same as in the original Call of Duty series. But they've also added quite a significant amount just for this specific game, which, again, they had to render to be as realistic as possible, which was a very big deal for them. A large part of what we worked on was sort of pushing the graphics design of things, so we had to really push high-level rendering, real-time shadows, bloom, other post-processing effects. Everything had to be as close as we could get it to the desktop version, which is, like I said, quite graphically expensive. And all of this had to be done at as high a frame rate as possible. We want to push the performance as far as we can get. We do want to aim for 60, and I believe we have been hitting 60 on a lot of devices. PC and console versions have been hitting 60 for years, obviously. So this is something we also want to push on mobile and make it as close as possible. So Call of Duty Mobile should be no different. It's the sort of what we were going for here. So a little bit on how it was done. We worked in collaboration with Tencent, so our name is on a lot of things here, our name being Samsung, and also with Unity on adaptive performance. This is what we really use to push the game to the limit, adaptive performance and Vulkan. The first thing I'm going to talk about is adaptive performance. So a bit of backstory, I guess, on the mobile limitation side of things. So mobile has quite a few limitations. I'm sure some of you in the crowd are quite familiar with this. The first thing is what we call thermal throttling. So on the right, you'll see some pictures of, over time, the temperature of the device starts to throttle. So after about 2 minutes there, I think it is 2 minutes and a half, the phone starts to get hotter and starts to throttle the frequencies. So this means that we get lower frequencies on the CPU and the GPU. It means we can run a much lower frame rate. It means that stuff starts getting cut out of the game. And we go from a steady 60 FPS, like we can see at the top, the bottom picture there is the FPS. It starts dropping after about 5 minutes. We start hitting down towards 40, 30 FPS. Our frequencies are going almost towards half of what they started at. So this is what we call thermal throttling. It's a huge problem because of the power in a mobile device goes from 100 watts on a desktop down to about 1 watt on most phones. So we have a lot less to deal with, a lot less to use, basically, to run our games. The second problem is, of course, power, like I just said. So we are working with 1 watt instead of 100 watts, and if we push that 1 watt as much as we want, we will end up getting extremely hot device. And while throttling is a problem because of 2 things. Firstly, because it reduces the performance of games, but secondly, because also it's in the user's hand. And if they're sat there and we let the device go to 100 degrees, I think it's quite obvious we're going to have some problems there. The final mobile limitation, as we put it, it's actually more of an Android limitation. It's something we call hardware fragmentation. So hardware fragmentation refers to the huge ecosystem we have working in Android. So we have, I think, thousands and thousands of devices now, all with very different specs, very different driver versions, very different hardware, and it leads to a very different experience on every single device you play on. So when a game developer creates a game, they create it with the device they're testing on in mind. And often this device doesn't actually represent the large part of the market, and we end up with games that look completely different to how the developer intended, running at completely different performance to how the developer intended when it actually reaches production. So I put there, optimization is out of the developer's control. This is not completely true, obviously, but it does put into perspective how difficult it is to design an Android game with performance in mind. So what is adaptive performance and why does it help? So the first thing adaptive performance does is it gathers data. So this is device performance data. So it shows stuff like the current performance and the thermal condition of the device, how fast it's running, and how hot it's getting. And then we can use that to scale things within the application. So we can use it to scale the contents, we can scale the quality of features in the game, and we can scale the frequencies of the device manually. All of this information comes from Galaxy Game SDK, so it's usable both inside and outside of Unity. So the adaptive performance side is a Unity thing, but Galaxy Game SDK reports this data, and it's actually possible to pick it up without the use of Unity or adaptive performance. So if this is something you're interested in, then yeah, very much possible. It is currently Samsung only. We're hoping it'll be picked up by more and more manufacturers as time goes on. We're not holding on to it or anything, so we're hoping it'll be a big part of the future of mobile gaming. So I'm going to talk a bit about power budget control. So adaptive performance supports a couple of features. One of them is power budget control. So this basically means that because a phone is an all-purpose device, right? It's not a games console. It's just a device we use for everything. It's not designed for long-term gaming workloads. So a common use for a phone is processing a photograph. So when you process a photograph on a phone, it just winds the clocks up. It throws them up as high as it can go. It says you've got 2 seconds of running it as fast as you can get it. And after that, we don't care what happens. So that's fine for a photograph. For a game, it means that when something suddenly happens in a game, it throws the clocks up. It starts running at like huge frequencies. Everything goes crazy, uses loads of power, gets really hot. And then the game is still running afterwards. And we end up with this huge frequency over time going up and going up way too high. And actually, it doesn't need to be going that high. It can be managed much better at some kind of like average position. So we care about this for games. And so one of the things that adaptive performance can do is we can give it a frequency cap, as we call it. So a frequency cap is exactly what it sounds like. In most cases, we want to just set the CPU to a limit. And so we'll say, in this scene, we want the CPU to run no faster than this. If it needs to run this fast, it can. If it doesn't need to, obviously it can go lower, as in some cases. But it means that we can average the performance a bit better. And if we're going too fast, if a frequency would be wasted, as in we're already hitting our frame cap, we don't need to be running a max frequency. We can scale it down and say, it's all right, just use this much. This is how much we need for this frame. The next feature of the Power Manager is also something called frame time tracking. So this is what I was talking about. You can measure how fast a frame is going. You can use this knowledge for a couple of things. So if you want to measure whether you need to run at a max frequency on CPU or GPU, you can use the frame time and say, okay, a frame is taking this long, and currently it's way below 30 FPS, if that's your goal. Then you can scale down the CPU and the GPU frequencies. Same, likewise, if you can measure your CPU and GPU time, you can find out which one is taking really, really long and which one's not. So if you measure your CPU to be running really fast and your GPU is running really slow, then you can tone down your CPU frequency because it's not taking any work, and your GPU is doing loads of work, tone its frequency up, and then obviously you've got more power to allocate to the GPU instead of the CPU, kind of on the fly, and depending on what your game is doing, this is pretty amazing. So one of our big examples of adaptive performance is the Megacity Unity demo. I'm sure most of you have seen this. It's a big city scene. It's got loads of flying cars, loads of windows, loads of houses. Both the CPU and the GPU workload are extreme in this case, so we can't just scale down one because the other one is not doing much, or we can't just use frequency management to solve this problem. So adaptive performance also supports something called quality scaling. What this basically means is you're taking components of your application and you're allowing them to be scaled down if the device is getting too hot, or if the device is pushing the CPU or the GPU too much. So this might sound bad, it might sound like you don't want your game to get worse looking, but we found that in most cases this is much more preferable to losing FPS. And it means that over time your FPS will stay relatively high, and you don't actually have to sacrifice much quality for it. So some common things, especially for the Megacity demo, we scaled the shadow and rendering distance, we scaled the texture level of detail, and we scaled the animation level of detail. These things are often a margin of only like 20 or 30%, so we're not scaling a huge amount down. We're not sort of talking you're going to see blocks or anything like that. Often it's like the shadow distance will go from like 100 to 80 or something like that as the device starts to get hot, and it just means the performance is leveled out a bit more, so that over time we lose a lot less FPS. We can also use the target frame rate. I've included that there, although it's a bit of an unusual one. So you can say that we want the device to only hit 55 FPS instead of 60 when it starts to get above this temperature, just so we don't start maxing out the temperature too much. So this is the results, basically. This is for the Megacity demo, so running at 30 FPS with adaptive performance. Obviously, you can see that over a course of about 20 minutes, we're seeing an absolutely huge improvement. The quality is scaled marginally, about, like I said, 20%, 30%. We're seeing an average of about 30 FPS, well, maybe 28 with the blue line, which is adaptive performance. Without adaptive performance, after about 3-4 minutes, it starts to really slump down. After about 10 minutes, 15 minutes, we start seeing less than half performance. And for what you're giving up in quality is completely marginal to the difference in FPS you're seeing from using this. So it is now available in Unity. Adaptive performance is available as of Unity 19. It's part of the package manager, I believe. And you can just build it straight into your game. It uses something called the provider system, which gives you easier ways to support more devices in the future. So currently, you'll see Samsung Android is the only one listed. But we hope in the future, more devices will be able to support this, and then it will become more of a common thing. In terms of what devices do currently support this, currently we're looking at very recent devices like the S10, the Note 10, the Tab S6, Galaxy Fold, anything that supports Game SDK 3.0, which is only the new devices at the minute. But by the end of the year, we're hoping that anything Android Q upgrade available will also have Game SDK 3.0, which means it will also be able to use adaptive performance. So let's bring it back to Call of Duty. Adaptive performance is an extremely new feature, like I said. So it's in Unity 2019. I'm sure you can guess Call of Duty Mobile wasn't made in Unity 2019. It's already released. Unity 2019 is maybe just releasing 0.3 or something like that. So Samsung, as one of its motives for the game development team, is to introduce this to as many games as possible. We are happy to implement it into older engines. So in this case, Call of Duty is using an older version of Unity. And we implemented it on the engineering side from Samsung, which is something completely cool. And if anyone wants to do that, we're also looking for people to do that with. We're very happy to assist with that implementation. So in terms of Call of Duty, we scaled the shadow distance, the foliage level detail, the animation level of detail, and the target frame rate. The target frame rate we use to determine whether or not we can reduce the CPU or GPU level, and all of the other ones we just decreased as the device got to get hot, like I was telling you earlier. So the power management techniques, we also used something called bottleneck detection, which is like I was talking about when we use the measure of a CPU time, measure of a GPU time, and then whichever one is the worst, we give more power to. So we use that for Call of Duty. And we also use just general CPU and GPU power budget management, which means, this is not doing anything, so just scale it out and don't make it work too hard. The parameters for this and sort of what we got from it, so particularly shadow distance is really good. We felt like there wasn't a huge difference in what you actually lost or /gained from this. So we actually got up to 10% CPU work was offloaded as we changed the shadow distance from 80 to 50. The foliage and animation level of detail were both relatively low detail changes. So the animation we changed by about 2 to 0, which gave us a small change of 0 to 3 on CPU and 0 to 1 on GPU. Not huge. The foliage level detail was really good and didn't actually make a huge difference to the game, which was up to about 5% GPU work time. And as for target frame rate, we added because we wanted to give more of a share when it came into really long times. So we were talking about like 15, 20 minutes of gameplay. We did just scale it down to 57, which isn't much. It's about 3 FPS. And we got up to 5% CPU and GPU save time on that, which when you're talking about 15-minute or 20-minute gameplay time is actually really huge. And that's the result for that one. So median FPS results were about 7%, going from 54 to 58 FPS. We also saved about 7, almost 8% of GPU time, which was really cool. And this is over a long period of time, so we're talking like 15, 20 minutes of gameplay. Stuff starts to really change, and adaptive performance starts to really kick in. There's more results on what we got from the power management. So we actually, on average, we're about 2 or 3 degrees cooler with ADP. And the frequency is on the right. You can see that the CPU is much more managed, much more average. So the blue line there is not as crazy and jumping up and down every 2 seconds, wasting frequency. And the GPU is like almost completely stable. So it's completely flat and is not wasting any energy when it shouldn't do. So that was the adaptive performance section of my talk. Next thing I'm going to talk about is Vulkan. I'm fairly certain most people in this room know what Vulkan is. It's Khronos' latest and greatest API. Chris, unfortunately, is not doing a talk on it this time to give you a huge introduction to it. So I'm going to discuss first I'm going to discuss what we see as our general Vulkan optimizations at Samsung. So there's some things that every single game we look at, we find that people are doing wrong, or on average are doing wrong. These ones will be quite familiar to a lot of people in the room, I think. And then I want to go into detail onto some of the key optimizations we made for Call of Duty regarding Vulkan and whether we actually made a difference with them and why we did them. So some of these will definitely look familiar to you guys. These are some of the things that we see every single game comes through to us, has problems with. And hopefully I'll be able to give them as like a general tip and remember these when you leave, when you remember these when you start developing a game. So the first thing I want to talk about is pipeline barriers. This is a very common mistake, and of course it makes sense that it's a very common mistake. Pipeline barriers are a synchronization point, and often that is a dangerous thing for a programmer when they're making their game. People program them defensively, so as soon as they start programming the game, they say, okay, this works if I leave these two parameters, so I'm never going to touch it again. I'm going to leave it for forever. I'm not going to check whether it's optimal because it works. And I think that's quite reasonable. Unfortunately, they can make a huge difference. And so we say that after development, before you release your game, come back and see if you can actually make something different. So in the example I've given you on the screen there, we have a source. So for those who don't know, a pipeline barrier is an execution barrier with a dependency to what came before and what came afterwards. So you tell everything in the destination stage to wait on whatever comes in the source stage. So if your source stage is fragment shader and your destination is vertex shader, it means that everything in the vertex shader has to wait on the finish of execution of anything in the fragment shader. Pretty simple. But in this case, you'd think that would make sense because the vertex shader should have to wait on whatever comes from the fragment shader. But often it doesn't have to. And in this case, we're actually giving a hard line between all execution before and all execution afterwards, when things could be actually overlapping here. So if we change this to source destination color output and destination out as fragment shader, we get this, which actually looks as a lot better. So things start to get overlapped onto each other. Anything in the vertex shader that can run without the fragment shader starts to run without the fragment shader, and anything that's in between the vertex shader and the fragment shader starts to run quite happily. There's a lot of cases like this. It's extremely common. So stuff like transfer, whenever you're doing any image transfers or buffer transfers, people often leave that too early. Same for color attachments and presentation transfers. The general rule of thumb I give is when you're doing an image memory barrier for an image, make sure you know where the image is going to be used. So if it's going to be sampled in a fragment shader, then make sure that the destination is fragment shader. The destination is fragment shader. Make sure that nothing else is waiting on it, and always just leave it as the destination is where you're going to use it. As a second miniature optimization to pipeline barriers, and something we see quite commonly in game engines, make sure you're batching your pipeline barriers. When we see like 5 or 6 in a row with like different resources in it, there's not really any reason to do that because they can be batched very easily into an array of barriers, and there is a fairly significant CPU cost involved in applying a synchronization point. So just as a quick and easy save, batch them all up into one, and you get fewer VK calls, which is great. So I've put it here that this one gives up to 40% performance. I think that's quite generous. We have seen a case where it gave about 55% performance in like seriously inoptimal barriers. Generally, I think the average is more like 20% of a performance increase. But however, yeah, this is something that's really important, and always go back and check on if your game is actually doing this optimally. So the next thing I want to talk about is load and store ops. You've definitely heard of this one before. If you've programmed with Vulkan, it's a core point, especially for mobile. So I've put here, you don't always have to care. I think that's the easiest rule of thumb with this. For those of you that don't understand what this means, don't care is a load operation for attachments, render passes. So you can choose to load it, you can choose to store it, or you can choose to don't care for either of them. This basically allows the driver to just do whatever it wants with the information. It doesn't have to save it, it doesn't have to load it, it doesn't have to clear it. It can just leave it as undefined. And it saves a huge amount of bandwidth because it means we don't have to load data from memory. It also means we save a bandwidth from storing. And it also saves any overheads involved with writing or reading that information and doing anything that the driver has to do for clearing it, that sort of thing. So this is actually mostly a problem because of people moving from desktop and console to mobile. So on desktop and console, this is not an issue. Bandwidth is not a problem, or at least not as much. On mobile, this is really huge and is often something that actually becomes a core bottleneck for an application and people don't realize. So always, basically my rule of thumb is if you don't care, then obviously don't care. A lot of the time you can just try this and see if your application breaks when you don't care. It's the easiest way to check. Not a very good debugging strategy, but it works. I put here that you can get up to 50% bandwidth. Again, this is from a case we had where everything was loading and everything was storing, and we managed to change about half of it to don't care. And this was a huge improvement for the game, a huge FPS increase for the game. And usually you don't get this big, but it's still something you could definitely optimize in your application, and you will actually see performance increases. My third general Vulkan optimization tip is cache stuff. So this is quite vague, and it comes in two parts. So the first one is something called VK pipeline cache. This is something that exists in Vulkan already. It's very easy to use. When you first create your Vulkan pipeline caches, it takes minutes, could be like 3-4 minutes. This is load time for your application. If you use VK pipeline cache, it means that it will save it to memory, and then basically when you run your application a second time, rather than doing that recreation, taking 3-4 minutes of creation time again, it will just do it straight away, basically. It will just load it from the pipeline cache. It's very easy to implement on a Vulkan developer side, and it's kind of like a free win. You'll be saving minutes of time for your developer every single time they turn on their application. The other thing I want to mention about caching stuff is kind of, especially for big engines, this is a big point. Use hash maps or std unload maps or something like that. Store all your descriptor sets, all your pipeline state objects, images, anything you can into maps. It means you don't have to update objects every time. So if you're using descriptor sets, for example, you can map them, and then every time you want to index it to the map, you can use the image or the buffer that you're actually trying to pull out the map as the index. And this means that you can just easily, quickly pull stuff in and out to make use of descriptor sets, and then just rebind them rather than updating them every time and changing what's actually being pointed to by the descriptor set. So this one's a relatively small optimization. I'd be looking at about 5% to 10% CPU time. It's also not the easiest optimization to implement, but I think it's sort of something that if you're really looking to push your performance of your application at the end of development, definitely something you should look into. And actually, I think it's really cool. So I've got 3 more general Vulkan optimizations to talk about. The first of one is something called wait for fence. It's a pretty common part of the Vulkan spec, sorry. So wait for fence, you use pretty much every frame, especially when you're presenting and waiting for images to be acquired. Often you end up with waits being stalled in your application because if the timing is not ready, if images are not ready and all the fences are in use, then you get stuck on a wait for fence call every time. So something that we suggest is actually to try and avoid that and make use of pools of command buffers / fences. So rather than allowing the GPU to stall on the wait for fence, you can simply pick another one that's ready or create another one that's ready for this express purpose. So again, this is used as something kind of like a pool of fences, like a map of fences. You check the status. If it's not ready, then you create another one, push it back. If it is ready, then you just use the one that's ready in the pool, and you keep going round and round. Eventually, you end up with about 4 or 5, usually maximum, in the pool, if it's a really, really busy application. So I think this is generally less than 10% general FPS performance increase. It's quite a generic and general performance increase. It's obviously only effective for really busy applications. In most small applications, your fences are always going to be ready anyway, so it doesn't matter. My 5th general Vulkan optimization is to do with render passes. So this is actually quite a small and I think relatively simple one, but it's something we see quite a lot from new developers of Vulkan. So they quite often fragment their render passes and create loads of smaller render passes to say, like, for this area, I want a render pass that renders this. Then for this area, I want another transparent render pass that does it for this. And then if I can have a post-processing pass for every single one, I end up with loads and loads of render passes, loads of CPU overhead of switching, beginning, ending. The important thing to say here is just don't fragment your passes. Almost all applications, you can have a opaque pass, a transparent pass, and then as many post-processing passes as you necessarily have. A lot of post-processing passes you can combine, but generally that's as much as you should ever have, and try to avoid having more than that. Don't want to see like 20 render passes because it's like different areas of the scene or anything like that. It's just kind of a waste. So this is kind of a simple one. Don't fragment your render passes. You'll be saving CPU performance up to about 5%. I think you can actually get more than this in some really bad applications, which we've seen. But generally, people are more smart than that. But maybe next time. The final general Vulkan optimization is also kind of a general programming optimization, I suppose. I put it as put stuff on threads or thread stuff. And this is very, very general. So in Vulkan, stuff is very easy to thread. It's extremely easy to use multi-threaded rendering for Vulkan, and I think you should. There's no reason not to, especially when I go on to talk about some of the Call of Duty things. The way we've used threads just for some really simple stuff is actually making huge differences to the game. It's extremely effective. And generally, you can assign just like a single thread for a specific task. I will come back to more about this in Vulkan specifically later, but just be aware of your application, how threadable it is, and try and make use of that wherever possible. So I think those were all of my general Vulkan optimization tips. If you are starting to develop a Vulkan application and you want to learn more about any of these that I've just spoken about, I have been quite vague, so I'd be happy to have a chat about them if you're interested. So Call of Duty was quite an advanced game, and obviously it works with Unity, which has quite an advanced rendering side. But we still found several places that the original version of Call of Duty actually had some quite extreme bottlenecks, and some of the things we actually found relatively easy to fix. So we spent quite a lot of time working with Tencent and putting stuff into the Vulkan engine that pushed it to, well, basically be faster than GLES by a considerable margin, and also to make the best use of the CPU and GPU threading that we had. So I've got a list of some of the optimizations here. I think there's 7 or 8, yeah. This is not everything we did for Call of Duty. It's actually a quite extensive list, but these are some of the things that I think are the most interesting and the most unusual Vulkan side optimizations. So I'm going to go in and sort of talk about each one individually a little bit. So the first thing that we did, or no, this is not the first thing we did, the first thing I'm going to speak about is the single scratch buffer. So at least in the version of Unity we had, they were using a big pool of scratch buffers and allowing them to resize individually each time. So you end up with like an allocate and a release and then a reallocate every time one of them needs to be resized. So you end up with like 7 or 8 buffers, each of them being reallocated and resized and then recreated. We thought that was a bit wasteful, and actually if we know in advance what objects we're going to be used, we can tell exactly what size of buffer needs to be used. We can just completely say it's going to be this big, and then you generally end up with, it's only recreated during the first load, and all allocations can go straight from left to right in this imaginary visual buffer. You put stuff at the beginning, it fills up towards the end. If there is a case where for some reason you have to add more, then you do go through the release and recreate process. That's quite rare. In our case, we didn't see it at all because we knew how big it had to be. And it just means that you end up with quite a huge CPU saving because you don't have all these small fragmented buffers recreating and re-releasing. You just have one that you continually put space into. So the next one is an example of threading that I was talking about. This is something with Vulkan that is extremely simple, is putting stuff onto other threads. So in this case, we used something called the low priority destroy thread. So this is just a separate thread that's created to do VK destroy calls, basically. We assigned it extremely low priority, so it just waits until there's space on a small core. When there's space on a small core on the phone, it just says, okay, just shove that in, destroy the object now, but don't let anything else waste for it, basically. So originally, loads of stuff was waiting on VK destroy calls that were being allocated into the queue of commands for Unity to go through. And this just allowed us to ignore those, basically, and still let them happen, so garbage collection is still happening. But it's not causing an actual bottleneck in the application. It's not holding up any of the main rendering or any of the main processing. So this is kind of similar to what I was talking about earlier about batching and caching everything you can. So we found that Unity was using an extreme amount of VK update descriptor set calls because they weren't using any of the descriptor set batching I was talking about earlier. So we were seeing that every single draw call had an allocate, an update, and then a bind descriptor set, which is extremely wasteful. So rather than doing that, we want to cache and reuse these sets. So we know that this set will always point to this resource, this set will always point to this resource, this set will always point to this resource. And then rather than allocating and updating them before each draw call, we just allocate and update all the descriptor sets at the start. And then every time a bind and a draw happens, we can just pull it out of the map, reuse that descriptor set, and redraw every time. So you end up with this happening, going to this happening, which is much smaller CPU overhead because we're always aiming to reduce the number of VK calls, which is exactly what happens. So this is an extremely simple one. So like I was talking earlier, we want to don't care as often as possible. In Unity, when a render target is being fully redrawn, it's still loaded, even though there's absolutely no need to, because obviously it's going to be redrawn and all the information is going to be wasted anyway. So for us, this was mostly post-processing effects, rendering operations that were taking up the full viewport were being loaded into from main memory, and we could just don't care and just ignore the result, and easy bandwidth save. We saved the bandwidth. It actually gave us a direct performance increase in our case of Unity, because it was a bit bandwidth limited. It also saves power, which is something we're always trying to do on mobile. This next one is another threaded optimization example. So we basically created a second thread for exclusively making threaded present calls. Sorry, just present calls, so VKQ, present, KHR, basically. This allowed render work to continue to go while the present was happening. So often present can actually stall the pipeline because it's waiting for an image to be ready or something like that. In our case, the thread that's actually stalled is just the threaded present thread, and the render thread can continue doing its own work. We do have to do a little bit of synchronization here because obviously we don't want the render thread to become more than like 3 or 4 frames ahead, and then we end up saving loads of data for the present call when it's ready. And we also obviously don't want the present thread going ahead when there's no work for it to actually present. So there's a little bit of two-way synchronization there to make sure that neither of those cases happen, but it's relatively simple to implement. And actually, I think this is available to almost every Vulkan application. So this is actually something that you should do if you can. It also actually remedies a very specific Android surface flinger problem, which surface flinger randomly blocks when calling present. So in this case, we can avoid that problem because only the render thread, only the present thread will block rather than everything, which is handy. So vertex buffers and index buffers binding. In Unity's case, it's a very big engine and it's extremely difficult to tell what's coming through it, basically. So we often get loads of draw calls coming through. We don't know what is being drawn when it comes through the engine. So in our case with Unity, we actually found that there was an extremely large number of vertex buffer and index buffer binds because drawns weren't being indexed when they should be. Because there's still no way for us to know if they should be indexed either. We don't have that information, same as Unity. So we actually just, rather than combining draw calls, we just reduce the number of binds that are happening for each draw call. So if there's multiple draws that are doing the same thing, basically, we just checked whether the buffers were the same as the previous call. So if the vertex buffer and the index buffer that we're about to bind is the same as the vertex buffer and index buffer that were already bound, then we can just skip those calls. And it's something, but it's basically a workaround because Unity is so vast that it's something we'll never know what's coming through. But it means that we can save quite a lot of time from the CPU side. So this is probably something you wouldn't really experience in general game dev, but it does come into play when there's very large engines such as Unity or Unreal. So our final Vulkan modernization that I'm going to be talking about today for Call of Duty is something we call direct buffer access. This is partly mobile specific and partly just because we know what's coming through. So originally data was copied to a temporary memory and then was accessed from another thread in Unity. Because we're using multi-threaded rendering with Vulkan, all resources can be accessed from any other thread, which is completely fine. And also we have unified memory access in Android, at least for Samsung phones, which means that all data can be accessed, whether it's device local or CPU coherent, it doesn't matter. All memory is always coherent, basically. Which means we can skip this copy operation. We don't have to have this extra buffer. We can just do it straight from the upload and then copy it straight into the final device buffer. Saves the copy operation, saves a bit of time. Again, this is a very Call of Duty / Unity specific example where it was doing this. But it was easy for us to do. So that brings us to where we are now today. Activision and Tencent, I think, did a pretty amazing job with Call of Duty Mobile. If you haven't already been made aware, it's extremely successful. I think its first week was a record-breaking number of sales, which is amazing. The combined work of Samsung and Unity with the Vulkan implementation and also adaptive performance brought around, I think, about a 10%, 20% performance improvement, which was amazing. It's obviously months of work, but it's something that was really cool in the long term. Adaptive performance is in Call of Duty from release for Samsung phones, and Vulkan will be coming in another patch towards the end of the year. which is where we are today. So before I go away, my boss told me I had to do like a 3 takeaway thing. So I'm going to do a top 3 takeaways for general Vulkan programmers. The first one is use adaptive performance. I think I made pretty clear that it's fairly simple. We can help you to use it if you don't know how to use it. It is very easy, and it's a very long-term gameplay. It's just easy wins for performance, basically. You are going to be seeing better long-term performance in your game without burning the user, which is something I think we all find quite important. Number 2 is referencing back to my pipeline barrier examples. Do check your barriers. If you're at the late stage of your development, do just go back and have a look and say, am I using the most optimal stages, or am I blocking my application? In most cases, you might be doing a very small block. In some cases, it's a big block, and you can change a lot. Number 3, check your load store ops. Again, if you don't care, then you don't need to care, and don't care. So never load or store when you don't need to. Try not to care. I actually had 4, so I told my boss I was going to do 3. So this is 3.5. Thread everything you can. Thread represent and destroy threads were a really great example for us in Call of Duty, and there is more examples you can easily use in Vulkan, so please go ahead and try and make use of them. Other than that, thank you all for listening. I'm going to be hanging around for the rest of the next few days, probably with a beer in my hand now. My name is Benjamin Mitchell, so benjamin.m is how you can find me at Samsung. And also, if you're interested in general adaptive performance collaboration or general Vulkan collaboration, you can email the bosses at gamedev@samsung.com. Other than that, thank you very much. If you have any questions, please let me know.